Hello, everyone, ladies, gentlemen, and non-binary. I'm Amelia Thompson, your host of the Wurth Electronic webinars, and I am excited to be bringing this brand new presentation with Roland Kratz. Roland is a senior product manager, SMPS at Wurth Electronic in Germany. Today, we are going to learn the ins and outs of LED dimming, benefits and uses of MaG'c LED drivers, and also solutions for those high current devices with MaG'c LED drivers in our presentation, LED driving and dimming made simple with MaG'c power modules. Now, if you have any questions during today's presentation, please don't hesitate to ask them in the questions box, and our presenter will answer them at the end. If your question does not get answered, no worries. We are going to make sure that everything gets answered after the presentation. If you think of it later, simply reply back to the follow-up email you're going to receive from here for you at we-online.com. That's here, the number 4, YOU at we-online.com. As a reminder, because you registered for today's webinar, you will automatically receive the video on demand and the recorded presentation slides in the next 24 to 48 hours following the show. So I know quite a few of you are going to be asking, why didn't I receive it yet? Well, it takes me some time to actually edit that video. Also, make sure you register for our next webinar. It is the first custom transformers webinar. We are bringing them right to your desktop, your phone, your tablet, wherever you're watching from, on July 14th. Register for Transformers. How does safety affect your design? Of course, you can register online at www.we-online.com/webinars. And a huge shout out to our exclusive sponsor, our neighbors next door in Minnesota, Digikey Electronics. Of course, they are the exclusive sponsor for all Wurth Electronic webinars, and you can find Wurth Electronic components online at digikey.com. I'm now going to hand it over to Roland as he presents LED driving and dimming made simple with MaG'c power modules.
So thanks, Amelia. I prepare my screen. So I hope all you see my screen. Welcome to the webinar, LED driving and dimming made simple with MaG'c power modules. I am Roland and Senior Project Manager of Würth Elektronik. This webinar today will have a time duration of 35 to 40 minutes and is about our LED driver, how it operates, how to use it, and I will show different ready-to-test solutions for LED driving by using power modules where the regulation is where the voltage regulation is turned into an LED driver for higher current. The agenda consists of following points. First, I will talk about the requirements for driving LEDs, then the benefits of the MaG'c LED driver, then the operation of the MaG'c LED driver and the option for dimming. Then I will show you solutions for higher LED current with MaG'c power modules. And also we have a MaG'c multi-color reference design consisting of our LDHM LED driver. And I have an application example. And at the end, I will show you our lighting development kit, which also consists of our LED driver. So we start with the requirements for driving LEDs. On the right side, you see the typical characters of an LED, and LEDs have steep forward voltage to forward current characteristic within the operation area. The steep part here is commonly the operation area. And what you see here on the bottom, there is a vertical line at approximately 3.2 volts. If you apply 3.2 volts, you will end up in a current of 350 milliamps, which is commonly common for for a high power LED. The problem here is if you apply a DC voltage of 3.2 volt and you change this voltage within a small area, you decrease it, you increase it in small area, you will move this operating point in a much larger range. This means the operating point moves in a very large range. So this can end up in overpowering the LED. For example, if you have a 350 milliamps LED and you increase your voltage too much, then you will exceed the maximum ratings for the LED, which is, let's say, in this case, 500 milliamps. And also, if you manage it to have a really fixed voltage applied at the LED characteristic, which is drawn here in black, moves also with temperature. So the best way is to stabilize the LED current. This is commonly done with a series resistor for low current LEDs like signal LEDs. But this creates extra power loss. For signal LEDs, this power loss is not that huge. But when you have high power LEDs, this is very significant. So the best way for high power LEDs is to use a constant current. An LED emits photons at any operation point along the LED characteristics. Less current means also less brightness. And also what is very important, if you need to maintain a specific light, a specific color temperature, which means also that the chromaticity coordinates of the LEDs has to be maintained. Then you need to stay at a fixed current and use the brightness at this point. For example, if you use a 350 milliamps LED and you choose 350 milliamps, then you have to live with the chromaticity coordinates. This means with the color temperature at this point. If you have a customer, for example, wants a specific wavelength, a specific chromaticity coordinates, then check the data sheets where these chromaticity coordinates are located. This is maybe, let's say, for simplicity, 320 milliamps. Then you cannot use this for 350 milliamps. You have to go to the current value, which gives you the chromaticity coordinates you want to have. For example, for a pocket lamp, it does not matter which color temperature you have. You can choose, for example, 3 or 4 steps that your pocket lamp can be dimmed. If you are in a car production, for example, at the overall inspection of the car finish, then you need specific wavelength of the color of the light to see damages in the finish, for example. Then chromaticity coordinates has to be maintained. Before we go into details, I will show you the benefits of the MagIC LED driver. Here you see the MagIC LED driver. This LED driver includes all components which are inside this red square. External is only input capacitor and the LEDs, and also the output capacitor is optional. You can put it in for better EMI, but it's not needed for operation. So with all this integrated, you have faster development cycles. All components here are integrated into one package, which results in compact solution size, simple thermal design. You have a big exposed pads underneath the module. You have all integrated protection functions which are necessary. Everything about EMC is given in the datasheet. You have multiple dimming methods. You have high efficiency for sure, and you have an input voltage range from 4.5 to 60 volt, which allows up to 16 LEDs, and you can have up to 450 milliamps per driver. Here you see the backside, and the design steps are quite easy. Set the current for the LEDs. This means the DC current. This can be done by the value of this resistor connected between the ISET input and the ground. The resistor value defines the current within a range from 300 to 405 milliamps. As this LED driver is designed for the common 350 milliamps LEDs, there is a resistor inside at the I-fix pin. If you want to use only 350 milliamps, just connect pin 6, which is I-fix, to ground. Then you do not need this external resistor. Then adjust the connect the LEDs. Put C in front of the module. This is typically a 2.2 microfarad capacitor, MaglC, in the size 1210. Output capacitor is optional, and you can use the dim pin for dimming the LED. If you only want to have a DC current through the LEDs, then just leave this floating. The operation of the MagIC LED driver, you see a schematic of the LED driver simplified. And this MOSFET can be turned on or off, and we go fast through the two loops. If this MOSFET is at 0 ohms, you will have a current flowing here according to the red dashed line. The AC part of this current flows through the output capacitor. The DC part flows through the LEDs. Then this overall current charges the inductor and flow through the sensing resistor for the current. If a peak current is detected, then the MOSFET is switched off. The voltage across the inductor reverses, and the current of the inductor will flow the same way like before. So the freewheeling diode is activated, and the AC current will flow through the out, and the DC current will flow through the LEDs. It's called the flying buck topology, which has similarities with real buck converter. So you also have a short circuit protection. If you have, for example, 350 milliamps and you have 6 LEDs, which all have 3 volt forward voltages, you will end up in 18 volt. If one LED here has shortcut, then you only have 5 LEDs with 3 volt, means 15 volt. And you see here a measurement starting with 80 volts overall, the sum of all forward voltages with 6 LEDs. At this point, one LED has a shortcut, and immediately the voltage across all LEDs is reduced to 15 volt, which is 5 times by 3 volt. Also, you have a LED filter protection. If, for example, an LED is open, this means, for example, it is burned for some reason, then the loop here is open. Before we had the 18 volt and 6 LEDs, 18 volt, like in the top example. Now we have an open loop. This means no current can flow. The regulation wants to maintain the current which flows before. This regulation increases as much as possible the voltage to get back to the 350 milliamps, but this is not possible because of the open loop. So the output voltage from 18 volt goes up to the input voltage. This means the voltage at the output of the LED driver is equal to the input voltage. The LED's constant current is set with an IZ or IFix input. With an external voltage, which is here, the brightness can be adjusted also. This kind of dimming changes the chromaticity coordinates of the LED lights. So, as I told you before, use the IFix pin to program it exactly to 350 milliamps. If you want to use another current than 350 milliamps, or you want to change on the fly the current, then you can use this circuit attached to the IZ pin. This resistor sets the initial current, for example, 350 milliamps. And in some applications, when the LEDs are aged, the chromaticity coordinates also shifts. This means the color temperature shifts. Then some applications require a new recalibration of the light. This means from a digital analog converter, for example, the voltage here can be changed to change inside the application, also inside an already operating application, the LED current to move the actual chromaticity coordinates to the requested coordinates, that the color temperature is back to the normal, like the circuit is new, like the LEDs are new. Most common is just to connect IFix to the ground. In my opinion, 98% of all of the application, you can just use IFix to the ground. With this circuit, this is a special application if you really use the same wavelength. Like my example before, if you want to check with a specific light the finish of the car. The dim input switches the LEDs on and off. With this, you can dim the LEDs. To summarize this, with the current setting, where my mouse is, you set the initial brightness. You set the DC current through the LEDs. And while you have a PWM signal, which enables and disables the driver stage, which enables and disables the LED current, you can dim from the initial current down to 0. To not see flicker, choose a frequency of 100 Hertz or more. The options for dimming. The first is the analog dimming. It's a real good dimming, especially for signal LEDs. but also you can use this with high power LEDs. One example is you have, for example, a specific voltage of 5 volts here, and you have 2 LEDs with a forward voltage, for example, of 2 volts each. Then you automatically will have 1 volt across this resistor, and you can adjust with this resistor a DC current through the LED. For example, when you have here a variable voltage source, you can just set the LED current from 0 to maximum. In other words, think about an LED and you will have a DC current of 100%, which can be, for example, 350 milliamps. This will give the maximum brightness. 80% of the current will give you 80% of the brightness, also the example 20%. This is the easiest way for dimming LEDs. Most common is the pulse width modulation dimming. It will look like that you have a fixed frequency consisting of the on time and of the off time, and the ratio between on time and off time will give you the brightness. What you see here is during on time, you always, also with 20% brightness, with 80% brightness, also with 100%, this is a DC current, you always will have the same frequency, also here consisting of on time and off time. You will have the same current, which means the same color temperature, the same chromaticity coordinates. The advantage is really here, you have from 100% brightness up to close to 0% brightness, in this example 20%, always the same color temperature. If you have a customer which has the specification, chromaticity coordinate needs to be maintained, then PWM is necessary, or pulse frequency modulation from the next slide. Analog dimming, just moving this 100% as a DC current down to 80%, 50% as a DC current, will shift the chromaticity coordinates. Another option is the pulse frequency modulation. It also affects the brightness according to the on time and the off time. But you see here, as this is a burst of pulses which are close together, and on the right side you see bursts which are far away from each other, so the off time is enlarged. This results in different frequency. If you use this, for example, check that with the lowest requested brightness, that you're not below 100 Hertz. The advantage is, especially at higher brightness, that you are at much higher frequencies. For example, when you need to dim light for television cameras, for example. Also, you can use a combination of analog dimming and pulse width modulation dimming. Analog dimming allows practically infinite dimming steps, so you can theoretically move it to infinite number of levels. PWM for lower current gives you the option of much more dimming steps. For example, if you have a timer in your microcontroller with 256 steps, and you dim from this current down to 0 in 256 steps, you have much more accuracy and finer steps as when you start from the high current, the 100% current, and go down with dimming only with PWM. But from the 100% brightness to 30% brightness, the chromaticity coordinates will change. And when you start from here with PWM dimming, then the chromaticity coordinates will stay like as the 30% brightness DC current. For sure, you will have more complex control necessary, but this is all included in nearly all of the microcontrollers available on the market with the timer stages. We also have ready-to-test solutions for higher LED currents with MagIC power modules, which acts also as LED drivers. I will show you this also in more detail in the next slides. This is our LED driver, the LDHM, which I talked about at the beginning of this webinar. For higher current, you can use 2 LDHM modules in parallel, so that you can achieve up to 900 milliamps. With these 2 reference designs, we use a power module which is a buck regulator which has a voltage regulated output, which means the feedback resistor divider, which gives the output voltage back to the feedback. These modules of this PCB and this PCB are used initially for generating a constant output voltage. So this is not really practically to drive an LED. So we have a circuit. This is linear regulator. This powers operational amplifier, and the operational amplifier here just measures the current through this resistor and tunes the feedback in that way that the constant output current is achieved. This can handle this can give you a DC output current up to 1.5 amps, and to give you more features, we have the 3 amps magic current source consisting of 3 amps power module, and here you see also the current measurement resistor. You have here also a linear regulator for supply, which you can remove. You can supply the operational amplifier also from the input voltage, and this turns the regulated output voltage into a regulated output current. Also, what is possible to adjust a maximum limit of the output voltage. As you already know, if you have a current source and you remove the load, then the output voltage will go to the input, to the value of the input voltage. And if you want to prevent this, for example, if you charge a battery which has end of charge voltage, for example, 5 volt, then you can adjust here 5 volt as a limit, and with another jumper settings here, you can adjust, for example, 3 amps as a charging current. Then connect your load here, and automatically, when you connect your load, your LED is driven or your battery is charged, and when the adjusted voltage here is reached, the charging stops automatically. We have from this reference designs also reference design notes with the circuits, with description, with some notes, everything what you need to design this by yourself is inside. And also we have some webinars about this. Also, when you turn voltage regulated module in a current regulated module, sometimes you need to compensate the error amplifiers. We have a video about that because the compensation of this is not really difficult. Usually for the compensation, you need proportional factor and integrational factor, and here you only need integration factor. This operational amplifier is just an integrator. The first option, just put two power modules in parallel, which means just connect both inputs together, which is the red line, and put both outputs together, which is the blue line. Then you can supply your LEDs with a double current, as easy as that. The current can be set independently, and you can use a DC current when you have two in parallel from 600 milliamps to 900 milliamps. But you can dim from 0 milliamps to 900 milliamps with PWM. Oh, I was too far. This reference design is a very interesting reference design, which is made many years ago. This has an input voltage up to 36 volts and can deliver up to 1.5 amps because the PCB is quite small and cannot handle much power dissipation. If you want to have more current, you can solder this on top of a motherboard. Then you will have the necessary power dissipation through this ground area, for example. This gives a DC current, but also you can apply a PWM system, PWM signal, and you will get the averaged output current as a DC regulated current. You have enable disable function, power good signal, and this is ready for pick and place. We have a design note, reference design note, where the link is here given. And the next thing is the MaglC current reference design, which has the order code 178001. Oh, I forgot. The previous one have the order code 178001. This is our LGA16 power module where 1, 2, and 3 amps are available. For example, if you want to have an LED driver for only 1 amps, you can choose the more cost-effective version of this module. You can have here up to 18 volt, up to 17 volt output, which means sum of all LED forward voltages. You can have up to 51 watt, which is quite really much. And as I told you before, you can adjust here an output voltage limit, which is equal to a free of charge, no, sorry, not free of charge, end of charge voltage for battery charging, for example. And also you have the adjustable output limit. You have jumpers, the settings starting from 350 milliamps, 700 milliamps, which are the most common high power LED currents. Now I will show you the MaglC multicolor reference design. This is the reference design, and the order code is 178050. This consists of 4 times our LED driver, which you saw before. This is one channel of the LED driver. And these are 4 channels of the LED driver. You will have here a Bluetooth module. You will have here another power module which generates 15 volt for a reason, which I will tell you in the next slide. You have switches to choose the input voltage, for example, 48 volt, up to 48 volt, or the 50 volt, depending on the number of LEDs. This is a microcontroller which controls everything, also our mobile app, where you can adjust the colors of RGB white LEDs, for example, to generate all colors you want to have. Or you can enter the colors for the horticulture design, for example. Also, you can. This means you adjust here horticulture LEDs for the growing of plants. Except this microcontroller, all components are from Würth Elektronik, including the PCB. We also have a panel where you can adjust as an option to the mobile app all 4 channels and an overall brightness with potentiometers, encoders, and also with switches. One channel of this reference design consists of LDHM. We need a P filter in front of it to one need is for EMI purposes for sure, and as all 4 channels can be on the same input voltage, that the switching regulators does not disturb itself for switching regulators. We need always a decoupling filter, which can be exactly the EMI filter. This is valid for all switching regulators, not especially for the LDHM. Then we do not know what the customer does with the reference design, applying cables of 1 meter, of 10 meter, of 15 meters, and for example, for horticulture in a industry hall where plants are growing. We applied, in addition to the P output filter, also a common mode filter to lower the EMI. And as you saw in the previous picture here, the overall EMI is gorgeous small. The application example is exactly the horticulture design, the RGB white design with a lighting kit. You will have here an input voltage of up to 48 volt. You will have a power module which gives you 15 volt from this up to 48 volt. And with the switch, you can give the up to 48 volt or the 15 volt to the magic power supply. The reason is if you have only one LED here with, for example, 1.5 volt forward voltage, you cannot drive this by this big ratio from 84 volts to 1.5 volt. So the input voltage of 15 volt can be selected with a switch if you have only 1 or 2 LEDs. If you want to have a lot of LEDs like 10, 12, you can select the up to 48 volt. This microcontroller controls everything, the Bluetooth module, for example, the optional control panel, and what you see is a typical application for horticulture, for architectural culture. So horticulture LEDs, architectural LEDs can be used, and also this can be used for infrared LEDs for a lot of applications. The lighting development kit. This is a box which also can be ordered. The main PCB of the lighting kit is integrated, as you see before, with the 4 channels. And also controller, power supplies, LEDs, lenses is included in the spec. and we have, as described, the WE illuminate, pronounced V Illuminate app, available free of charge for your mobile app. Yeah. So, thank you for your attention, and many thanks for joining this webinar. If you have any questions after this webinar, please write to the Power Modules hotline. This is the email address here, powermodules@we-online.com. And if you already entered some questions, I can answer now your questions.
I'm going to go ahead and see what we have. Our first question here, can I use more than 2 LED drivers in parallel?
Okay. I think this is about the ADHM LED drivers, but I will answer this question to answer more up. Yeah, I will go to the LDHM slide, to this. So here you see 2 LED drivers which are connected together with the output, the output ground for the LED, which is LED minus and LED plus. This is an example of 2. You can put 3, 4, 5, or 10 together. It doesn't matter. But just keep in mind, also here it's written in small letters, if you have switching regulators in parallel on the same V-in line, I hope you see my mouse here, the V-in is tied together to 2 LDHM modules, then these have to be decoupled. So you need a decouple filter, which I showed here. This is an EMI filter and also acts as a decouple filter. You please put this in front of the LDHM, and then you can connect LED plus and LED minus of all 2, 3, 4, 5 LDHM modules, and it will work because this is a really independent current source. I hope this is correctly answered. Additional, I showed you this reference design, which also can be paralleled at the output, and also this reference design can be paralleled at the output to achieve, for example, 6 amps. So, Emilia, do you have another question? The next question,
yes,
please.
It looks like we have time for one more question here. And like I mentioned before, we do have quite a few coming in. And if your question does not get answered, we will make sure that we answer them later on through email. Our final question here, since this LED driver is basically a current source, is battery charging also possible?
Yes. This is the LDHM, and we have a constant output current. A constant output current can be used for battery charging or charging of a big capacitor, like a supercapacitor, for example, is also possible because all applications for LED driving, supercap charging, battery charging uses current sources. So yes, you can charge batteries with this. If you replace these LEDs with a battery, for example, please check the waveform of the current, and if you use trickle charge, for example, you can use the dim pin for that. but please put an output capacitor to bypass the inductor ripple to keep away from the battery. But in general, if this question, I do not know if this question is in general about the LDHM, I would highly recommend to use current source with an external regulation loop. Like this, you have an external operational amplifier here and here. These two, we have more reference designs like that, but these two reference designs are a much better choice for charging batteries, because you also can here adjust a signal which sets the current, and you can, for example, with this both reference design, for special batteries, you can have an arbitrary waveform of the charging current. You can like trickle charge or whatever with this. And also you automatically, with this reference design, you have the end of charge voltage. If you have any questions about battery charging or supercap charging, this is a complex topic. Just come to us as on the Power Modules hotline.
Okay, thank you very much, Roland, for presenting today. And also, everybody, thank you for joining us. Apologies for the technical difficulties, but we have been doing this for, years and years. We all know that things do happen. Again, if your question did not get answered during today's presentation, we will make sure that we follow up with you in the next couple of days. If you think of a question later, simply reply back to that follow-up email. It's here for you at we-online.com. And make sure you register for our next webinar. It's our first custom magnetics webinar on July 14th. Register for transformers. How does safety affect your design? Register online at www.we-online.com/webinars. And if you want to stay up to date on our webinars, don't forget you can always follow us on LinkedIn. You can follow our corporate page or my personal page. I'm Amelia Thompson, and I have mentioned this in previous webinars. We do have a podcast available. A lot of it is replays from our webinars. Just search for Wurth Electronic What's Up Radio Podcast. You can hear my charming voice every Thursday at noon. I'm Amelia Thompson. Have a great day.